Hi, I'm Sami. I'm head of Devrel at MegaETH, and I want to tell you guys a little bit, about why we're unapologetically performant. So I have a bit of okay, cool. So consider this application. You have a carrot on a stick, it's being moved by the user, and then the rabbit has to run after it. On a traditional blockchain, it looks like this. The video's not playing. Basically, here it moves at the block time is 2 seconds. Here the block time is 10 milliseconds. On this one, the rabbit jumps to where the carrot was. On this one, it chases it pretty closely. The only latency here mainly comes from network propagation. With that, I'd like to talk to you guys a little bit about the lifetime of end-to-end latency. A transaction begins on your browser, goes to the network, goes to the block producer, and then the time it takes for that to happen is the speed of light propagation latency. As a rule of thumb, it's about 100 milliseconds. From here to Sydney, maybe it'll be 150, but we think this is a reasonable number. The block producer needs to package it. This is the block time, and on Ethereum, it's about 12 seconds. Most leading L2s do it in 1.8 seconds, and that includes the time it waits to be packaged into a block, any sort of consensus overhead, and the execution. Then you need to wait about another 100 milliseconds to get receipt of the block. From this, we can see that latency can be broken up into two components. There's speed of light propagation latency, which is these two ends, and block time. Unfortunately, there's not much we can do about speed of light, right? For superpower users, they can co-locate next to our sequencer in the same database. Something like a market maker on an on-chain club. They can get speed of light latency in the tens of microseconds, but that's not really practical when it comes to commercial users. That's why at MegaETH, we're much more interested in reducing the block time latency. What goes into block time latency? So you have sequencing and DA, which includes any time wasted just waiting to be packaged, and then you have actual execution. Conventionally, sequencing and DA are done by a consensus algorithm. Now, let's say no time is wasted waiting for it to be packaged. You're still at a minimum going to wait for 2 messages to go around the world, which is inherently slow. What we suggest is to replace consensus with centralized block production. Now, because they don't need to coordinate with others to produce blocks, they can produce them at the most efficient pace possible. With frequent blocks, you don't have to wait for any. With more frequent blocks, there's less time spent waiting for transactions to be packaged into the next block. And then you can get 1 to 10 millisecond block times. Now, I suggest we get rid of consensus. Let me justify that a little bit. You can safeguard that by building an L2 on top of a decentralized L1. This was actually an idea that was proposed by Vitalik in 2021 in a blog post called Endgame, where he concluded that all scaling solutions lead to centralized block production. You can read the paper. It's great. We reference it in our white paper, but I'm not going to go too much into that part. What we at MegaETH find much more interesting is optimizations when it comes to execution. Before I talk about that, I want to give you guys a bit of an overview of our design philosophy. We believe that no high-performance systems can be built without first understanding the existing state of the art. You must measure, then build. That's why before we built anything, we did rigorous measurements of current execution clients like RETH. We wanted to see where they fall. We wanted to pinpoint where they fall short and where we can make the most impactful improvements. I'm going to go over an experiment over the next few slides. These are the test conditions, but I'll keep them so you can reference them as we go on. In this first experiment, we ran historic sync using a 512 gigabyte memory and persisted changes every 500,000 blocks. This allowed us to focus on execution layer performance without database I/O distorting results. The graph shows throughput in TPS against block time. The blue dots are real-time TPS, and the red line is moving average. Let's focus on the last 1 million blocks, as we think that's where you're going to have the most meaningful inferences. We see that in this area, TPS averages out at around 14,000. Is this low? No, of course not. But is it fast enough to build a world computer? We don't think so either. Furthermore, I mentioned we get rid of all other overhead. So this is simply from EVM execution. We thought, why does that happen? The main reason is overhead from interpreting smart contracts. Smart contracts are written in high-level languages like Solidity and compiled into EVM bytecode, which is only interpreted at runtime. Let me give you guys an analogy. When I was younger, I learned Russian as a child. I'm by no means fluent, but if I have a dictionary, I can put a sentence together. Imagine last week the organizers told me, hey, Sami, it would be great if you did the presentation in Russian. And I said, sure, but I'm not going to bother translating in advance. I'll translate when I'm up here. Obviously, it'll be a waste of everybody's time if I'm translating word for word. This is what we believe the EVM does at the moment. That's why we implement just-in-time compilation, which translates EVM bytecode into native machine code before execution. So instead of translating on the dot, I brought up my presentation already in Russian. Our engineering team ran the most recent historical transactions from ETH mainnet, and we found an average 3 to 5% time performance boost on smart contracts and up to 100% performance boost on the most compute-intensive applications. But I prefaced the previous example by saying we're only looking at execution overhead. We found that to be around 1.6 milliseconds. But unfortunately, conventional blockchains must also read and write from the database. That takes the vast majority of the time. But what we really want ideally is that block production only focuses on transaction execution. Let me give you another analogy. As I come up here, let's say I decide, yeah, I will translate in advance, but they say, why don't you do it in Portuguese? I don't speak any Portuguese, but fortunately, there's a dictionary on the other side. The way EVMs work at the moment, I would find one word I have to translate, run across the room, see what it is in Portuguese, come back, and do that back and forth. You guys would think, what a waste of his time to be running around. That's effectively what the EVM does, and that's the state access bottleneck. To address this, we cache the entire state into memory. This minimizes disk access and ensures that all data is at hand. Like me bringing the dictionary to my desk and actually spending all the time just translating, not running around. On a non-optimized blockchain, we find that EVM execution only accounts for 16% of the time spent. With in-memory computation, we've brought this up to over 90%. Okay, so I've explained how we can get a great blockchain. But why bother with an unapologetically performant blockchain? Well, beyond the bunny image I was trying to show you earlier. How many of you guys have seen this recently? Or ever? So why is this coming up, and why is it happening more frequently? It's because Netflix is doing a really good job at discerning and blocking traffic that comes from known VPN IP addresses. What if we decentralized VPNs? Right? What if I'm living in London and I decide I have all this unused bandwidth and I want to host a node? It would be near impossible for Netflix to discern that from regular traffic, right? It would completely blend in as usual. That's the benefit of diversifying VPNs, right? But the issue is, but then you have a problem. I right now pay NordVPN $10.99, and I trust them to give me a month's worth of service with some block bandwidth quota without interruptions. If I just have some stranger running the node, I don't know they're going to do that. Furthermore, when we decentralize things, there's no track record. And the way these things work, I'll always pay in advance, so I really have no incentive to cheat. I can't see what I'll get out of it. The node operator conventionally will be paid by the bandwidth they provide me. So they'll say, oh, I gave Sami 100 gigabytes when they actually gave me 5. And that's one of the biggest issues right now with decentralizing a VPN. How can we address this problem? One of the options is called proof of bandwidth. And that's 2 parts. The first one is meter monitoring, mutual metering, which means that I as a user will track how many bytes I receive, and the node will track how many bytes they send me. If these don't reconcile, then I'll have to switch to a different provider. Then you come up with the problem of, well, Sami, you paid for this in advance, so even once you switch, you've lost all the money because they cheated you. And then what you want to do is you want to reduce the duration of the service period. That can be addressed with settlement frequency. But that's where the performance really becomes important, right? Let's imagine a world where let's imagine a project where you have 10 million users and 20 million nodes. That's not unreasonable, given that's about 0.7% of the current VPN environment. If you wanted, on Solana, if you wanted to settle to the network, it would take 1.85 hours, which means it would take 1.85 hours for us to realize that I've been screwed and move on. On MegaETH, this would be done in 3.3 minutes, which means in Solana, you can settle 12 times a day and make 12 micropayments. On MegaETH, you can do it 432 times. Now, this is just one example of an app that's being built on MegaETH, which uses this. This is just one use case for high performance. Others are fully on-chain Minecraft, real-time sports betting, and real-time prediction markets. And a matter of fact, all these projects are being built on MegaETH, and this comes from a light paper of one of our projects. But importantly, these will only be possible if we unapologetically put performance first. Thank you.
Great talk. Thanks so much. Are there any questions for Sami?
Just curiosity, why you didn't put Polkadot on the list of comparison? Because Polkadot can reach really amazing...
I trust you're referring to the one with the VPN?
No, I mean, when you compared the Solana with MegaETH, where's Polkadot in this?
This was built by one of the projects, so I'm not super familiar with this exact table. They built it, I borrowed it from them, so I can't. But I can put you in touch with them, and maybe they have a good reason.
Yeah, I'm curious about like just trying to learn from, I'm mostly working with Polkadot. And of course, we learn from each other. So it's really nice to put the space advanced to learn from each other what we are doing and what others are doing and trying to apply some technologies in different projects.
Well, I mean, I'll put you in touch with the team, and then I'd love to also hear. Maybe I can make a group chat between the three of us and see why they made that decision.
Okay, thanks.
Any other questions? Larry?
So just a small detail I noticed, on one of your slides you showed a chart of like TPS when you do state sync. I noticed the TPS has been trending down over time, like it's just getting slower through the years. Do you have any take on why that's happening? Do you think it will keep going slower?
Yeah, so that's interesting. I think it doesn't necessarily have to do with, I don't think it necessarily has to do with over time, it's the amount of data, fewer state accesses. Because at first you had 512, sorry, this is a nuance that I should have mentioned earlier. The memory changes with that graph as well. But I wasn't very clear about that, I think. But I'll get back to you offline about that, because I haven't given that too much thought.
So I'm already building on MegaETH, and one of the questions I've been finding is how can I have a fast oracle, because Chainlink I don't think is provided by you already. So which oracles are you using to make this as fast as possible?
These are things that we haven't released yet. So we'll put this out in our tech docs that come out soon. But we're not really talking about these things at the moment.
Okay, I wanted to build like an options, like the zero-day option expiry, so I needed like really fast oracles. So I'm guessing they will come out in the near future.
Are you on MegaForge, or when you say you're building with MegaETH, which
so
channel?
I'm doing like a CDP.
Okay.
So it's like chain agnostic, but it's easy to do on MegaETH because I know some friends there that have been getting me to the way.
You should join our builders chat, because these are things that will be released there first.
Okay.
Yeah, but we don't have that information yet, given we're still in private testnet.
Thank you so much.
Yeah.
Thank you. Any other questions? I think we have one more. One more question.
Can we implement this without affecting decentralization? And if so, why aren't we implementing this on something like Ethereum?
So would you repeat that? I missed the beginning of the question.
If we implement this, will this affect decentralization?
No, because we build on top of Ethereum. So we inherit all the decentralization from Ethereum.
Okay, so why are people not implementing this into the Ethereum code?
The first step is reducing the consensus, right? The first step is moving to a central block production. And that you can't really do, I guess, on Ethereum.
Yeah, okay.
Great questions. Any other questions in the audience? We still have time. All right. Thank you so much, Sami.